Welcome back to another Roblox scripting tutorial. This is going to be a continuation of our previous video in which we created a script that, as you can see here, allows us to calculate and generate a Bezier curve. Then have our seagull here follow that curve using tween service. I'm going to try to pronounce the word more French the way that it should be. It is a name after a French name. In this video, we're going to be making some changes to that script and giving our seagull the ability to select where it flies to, generate its own flight path curve to that location, and then set its speed relative to the distance it's traveling. Enough preamble though, let's get this tutorial started. Alright, first thing we want to make happen is getting these three parts that make up our starting position, end position, and our curve control point all generated during runtime. To do that, let's first go ahead and delete the point A, B, and C that we have here in the actual workspace. And then we'll go into our movement script where we left off on the last video. We're currently still referencing these deleted parts, so let's go ahead and make sure to delete those lines in our code. We were then referencing those variables in our function call all the way at the end, so I'll make sure to clean that up. Now there's going to be one constant in all of our coordinate points for this curve we make, and that's the seagull's position being our starting point every time. So let's try and get our code working mostly as is for now, and then add to it from there. That means we can fill our first position of our flypath function by inserting gull.position. Gives us the position of the model, if you recall. We're calling the gull as the model of the seagull. Or the mesh of the seagull. And that's going to actually allow us to get the position of the seagull no matter where it is. So if it's here, it's going to generate a curve, fly to wherever it decided to fly to. And then let's say it decides to fly back here somewhere and it's over here, it's going to start from where the seagull is, generate a curve to get over to that. And since our seagull is going to want to be generating these curves each time it wants to fly somewhere new, we'll place that code inside of our create curves function, which is being called inside of the flypath function here. So every time we're doing this loop, our flypath function comes in and it's running this create curve in order to generate that curve. So that's why we're going to place our code in this. Now this, of course, it does take three positions, right? Our first position is taken care of. The second and third position of our curve parts are going to be generated, so we really only need to take in one argument into our create curve function now, and that is just our point 0. But I'm actually going to go ahead and call that start POS, start pose, just basically short for start position. And let's also make sure that we're changing that in our C-frame quad Bezier call here. Because as you can see, we've got these red lines because they're referencing positions that don't exist anymore in this case. So I'm going to remove this and replace it with that start position. Now I don't need to put dot position here because we're actually feeding in the position directly. And we'll also be changing the parameters in the flypath function to match. And now we can just drop this into start position. And of course this then just takes the start position. So pretty simple. Alright, so back in our create curve function, let me go ahead and shrink some things down so we're not overwhelmed with too much here. So in this one here, go ahead and increase the size of this a bit. So after our folder is created, let's generate those two missing points in a relatively simple way in order to ensure everything still works. Instead of making parts for this, we can create a new vector 3 for each and use those values in our quad Bezier function. For the time being, since I still want to visualize the curve itself, we'll keep using parts for that. Though if you wanted, you could also replace those visuals that you see here by us creating a part and everything with just replacing this with a vector 3, and that would just save a coordinate in the table instead of having to save a part. Again, we're just using the parts for debugging to basically see that our curve is being generated and what it looks like when it is generated. So for our control point, we're going to go ahead and call that variable, let's do it here. We're going to go and do local, and I'll call this control pose, so control position. For simplicity, we're going to keep the height of our control point consistent no matter the distance flown. Since we're doing that, let's make a variable up top here in our variables. For the maximum height our seagull is going to fly. So based on real seagull information, their average flight altitude is equivalent to 54 studs. And yes, I did far too much real-world research and math on this, so I'm going to note that as the default value, but for testing, let's keep it at 25 for now. So we're going to call this max height And this is going to be 25, but again, I'm going to note that the default is 54. And I'll even put that it's based on average flight altitude of real seagull. Alright, so it's worth noting, however, that this value isn't going to be accurate for how high the seagull actually flies, since if you recall, when we have a point here and a point here, and we stick a point up here, the seagull never actually flies up to that top point. It flies to the top point of the curve that we generated. So if we wanted to make it more accurate, we could go through more math or simply just overshoot the height so that the curve would be enough to get to the desired flight altitude, but I'm not going to be messing with that here. We're just going to keep it simple for now. So now let's feed our max height value into our control position vector 3. So we're going to be basing this off of our start position. We need to go start pose, and we're going to add a vector3.new, and then we will do 0, comma, and I will say max height, copy, and comma 0. Alright, so this of course places the control point directly above our starting point. But in reality, a seagull typically takes off at a shallower angle and lands at a steeper one. So ideally we want our control point to be closer to the end so that our curve looks more like this. So instead we're going to add some value to the z-axis as well. We want to base this on the endpoints location, so let's make the endpoint variable now. This variable is going to be before the control point so that we can reference it in our next calculation. We'll have that equal start position plus a vector3.new. And in the end, we're going to have the seagull randomly decide how far to go and where to go, but for this initial test, let's keep it on 2 dimensions, our y and z axes. In that case, let's give the distance of 40 on the z-axis. For the y, we can leave it at 0 for now since we're working on a flat plane as well. So let's go ahead and do 0, 0, 40. And when I inevitably take this further, I'll have to consider where the ground elevation actually is so the bird doesn't fly into the ground or land above it. But again, we're keeping things simple here. So back to our control point now. We can do a little math to always place the control point a certain distance between the start and end points. For example, if I wanted to have the control point always be 80% of the distance from the start point moving toward the end point, we can get the magnitude of our 2 start and end vectors and multiply that result by 0.8 or 80%, right? So in between here, let's go ahead and do local magnitude equals, and we'll in parentheses go end position minus our start position, and then we're just going to do dot magnitude on that, and that returns a positive number, which is the distance between those 2 points there. So now our control position, instead of having a 0 here on the z, we can go ahead and do magnitude, and we're going to multiply that by 0.8. So now we need to feed these new variables into our quad Bezier function. So if we come down here to where our quad Bezier function is, you see we still have these position 1, position 2. We're going to go ahead and replace those. So obviously our position 1 now is going to be our control position, and our position 2 is going to be our end position. So if I run this, you can see that our curve is generating exactly as designed, but the seagull's actually resetting, then playing sort of a leapfrog game with itself. Let's see it again here. And that's because when we loop our function, we're not removing the previous curve point data from the curve point table. So we're actually just adding new data, having the seagull reset and refly the previous curve before flying the new curve. That's a simple enough solution though. So just like, stop this. So just like we are destroying our curve parts folder at the end of our while true loop, we can just reset our curve points table to a blank table. So let's do curve points equals and just a blank table with 2 curly brackets. So if we run the game now, seagull flies from one point to the next, waits 2 seconds, then generates new data, generates a new curve, and flies along that curve. And we'll continue to do that infinitely at this point. So great, we're most of the way there then. What else can we do? Well, we have the seagull currently flying to a very specific point that we have set. But let's have the seagull select a somewhat randomized landing point within a certain distance of itself. So to do that, we need a couple more variables. So we'll come up top here under our variables section. And let's create a max distance and a min distance. There we go. And we can use the numbers we enter here to make sure the seagull can only fly so far each trip, but also use that min distance variable to make sure the seagull isn't just flying a couple meters at a time. So I'm going to settle on 20 for the min distance. And let's use 60 as our max for now. Working on just our 2 dimensions, this could be as simple as using math.random with our 2 variables for the end position's z value. But let's be a little more productive now and make sure the seagull can actually move anywhere on the XZ axis. So anywhere it wants, essentially. 360-degree range. So obviously we're going to be working with our end position variable. Since we want to select a different end position each time the bird lands, we want to make sure that the random selection occurs within the create curve function. So we could do this inside the end position variable itself instead of just having 40 here, just have a bunch of code. But I'd rather keep the code looking clean by making a new function. Up here, let's do a new function and we'll call it random distance. So quite simply, we're going to be making a variable called distance in here. Distance. And we're going to use math.random, I can type, and filling in, let's say, min distance and max distance as the 2 arguments there. So math.random is going to select a random integer between our minimum distance and our maximum distance. Right, so anything between 20 and 60 in this case. Now, we want to make sure we can also sometimes get a negative value, but we can't just use math.random for that directly, since it would return a value from negative 60 to positive 60, which would include values less than 20, which is less than our minimum distance. So the easiest way I'm going to get around that is a simple if statement that essentially flips a coin and will return either the positive value or the negative value depending on its result. So we'll say if math.random 1 and 2, so think of it like 1 is heads, 2 is tails, right, on a coin flip. So if our coin flip is 1, or is heads, right, then we're going to assign distance a new value, and distance is going to be whatever distance was times -1, which would then return our negative value. And if it doesn't, then we're going to, so if we get tails, right, if the math.random returns a 2 as a result, we're not getting a negative value, so we're just going to return distance. And the nice thing is that returning distance here is either going to return the positive value that we received, or if we get a negative value from this if statement becoming true, that changes what distance is, so when we return it, we get the correct value no matter what. So that's a super simple thing there, but here's where things get a little tricky. In order for our control point to follow along with the endpoint, right, because if we have our endpoint popping up at a proper height, that's fine, but in order to get it to also follow along the x and z axes along whichever way the endpoint goes, we need to change a couple of things. So first, let's go ahead and set an x and z variable to feed into both. So we'll just say local x, and this is going to equal random distance, and we'll do the same exact thing for local z equals random distance, and we're just feeding those values in. By feeding them in there, we're not only going to get a new number each time, but we get different numbers for both the x and z axis, just kind of increasing the randomness. So our endpoint now, our end position, is super easy. We just fill in x in the x and z in the z. But instead of getting magnitude now, let's go ahead and get rid of that line. We can just flip things around a little in the control position variable. So instead of coming from the start position, we want to come from the end position. So we're going to change that to end position. Right, that's going to be our jumping off point for our control point. Since we're now moving backward along our curve, we also need to subtract instead of add. And also, since we're now moving backward, we need to flip our percentage from a 0.8 to the opposite of that, which would be 0.2, right? Instead of 80%, it's 20%. And finally, we just need to use our x and z variables and multiply them by 0.2, and we'll do that here. So x times 0.2, and instead of magnitude now, we're just going to replace that with z. And finally, as well, because we are now subtracting, we need to make sure our max height doesn't put us underground and make this a negative value just by putting a minus sign in front of it, which subtracting from a negative obviously creates positive. It's a double negative. So that gets us there. Let's go ahead and run the game now and see if our bird is properly creating a curve following from start to finish. Okay, looks good. And you can see if we get to the side of it, it's the same curve that we generated before, flying at different directions. However, you'll notice there's a weird thing happening with our seagull, especially when it flies back this way on the z-axis, that it's flying backwards. It's always facing the same exact position. It's always facing this direction, no matter what. So this is because we're spawning our curve points without rotations, and we're tweening the seagull's C-frame to those positions, which means it's keeping the orientation of these blocks as well. So how can we fix that? Well, for me, inside of our fly path here, in our tween, I found that instead of doing a cframe.new, which uses one vector3 to a cframe.lookAt, which uses two vector3s, so it still moves to the position of the, if I move this in here you can see, it moves to the position of the first vector3, looks at, in other words, orients itself facing the second vector3. This seems to give a really good result if I then go, okay, we're still moving to here, but we want to look at, in this case, I'm going to do things a little weird. I'm going to do our start position, and doing things this way works for me specifically because the animations that I have for my bird, for my seagull, actually were imported backwards, so everything's flipped 180 degrees. So if I were to play the animation on the bird as it is and it's facing this way, when the animation plays, it's actually facing this way instead. So just doing facing the start position actually fixes the problem for me, and I can show you that if I run the game here. You'll see that he's facing the right way, and essentially his tail is always kind of holding the start position, which kind of gives a little more naturalistic look to its flight. Especially as it's coming down and kind of hovering down the way that it does. All right. So this is a really great result. However, doing this alone, unless your animations are also flipped around backwards 180 degrees, you're going to need to also include a way to flip the bird around, right? So this is actually a really simple fix. We're going to multiply our start position, multiply our cframe.lookAt by cframe.angles, and then we're just going to use 0, math.pi, 0. So on the y-axis, this math.pi is going to make it a 180 degree flip. So if I show you again with mine, you'll see that mine's going to be flying backwards now because my animations, right? However, if I were to, for example, comment out my animations so that it's not actually animating while it flies, you'll see that it is holding the proper direction the way it's supposed to. Alright, so let me go ahead and uncomment these. Get our animations working again. So this fixed the issues. We have this much more natural looking flight from the seagull. That's why I choose to use this method over other options that were available to me. Now we're nearly done. Thanks for hanging in there with me on this. The last thing we want to throw in here is a speed adjustment, or velocity really. If we generate a curve that starts at 0, right, and it ends at 40, a distance of 40, the points that make up the curve are going to be spread out a specific amount. But if we generate a new curve starting at 0 and ending at a distance of 100, because we're making the same number of points on our curve, the points are going to be spread out further. All right, so the problem is that our seagull is going to take our 0.3 seconds here to get from one of our curve points to the next, regardless of how far those points are from each other. That means it takes the same amount of time to fly 40 studs as it does 100 studs, or even 1,000 studs. So the speed's going to be very inconsistent. So I can even show how bad this gets if I set our curve points here to generate 100 points. and I run this, and you can see just how slow he's flying, because it's taking 0.3 seconds to fly to each point. But each point is so close to itself, or to its previous point, that it's taking a long time to get from our start point to our end position at that point. So obviously this is a problem. To fix it, we just need to do a little more math based on the default speed of our seagull in order to adjust our tween time accordingly. So again, I did way too much research on real-world seagulls for this, and I determined that the average airspeed of a seagull is equivalent to 24 studs per second. So after some testing though, I found this to be a little too quick for short flights. So we're gonna actually use 23 instead. So back up here in our variables, let's do local speed equals 23. And I'm not gonna worry about setting a default based on average and all that. So I misspelled that there. But we are gonna set the default as the 23 because I do find that to be a good number to go with there. But if we ever wanna mess with that later, we know what we started with, what we liked, and we can always change it around anytime. All right, so let's close our create curve for a moment here. Let's focus on our tween, right? So I'm gonna go ahead and create a new function. I'll create it right here. We'll go and do local function. And I'm gonna call this function speedcalc. We need to take 3 points into consideration, and for consistency, I'm gonna use P0, P1, and P2, just like we were using before. And let's first calculate the total distance the bird is going to travel. And we can do that by getting a magnitude of 0.1 minus 0.1 to 0.0 and adding it to the magnitude of 0.2 minus 0.1. So the reason we want to do that is because, keep in mind, the distance the bird actually flies is further than just from the start point to the end point, right? It has to fly all the way up here and down to here. So that's going to actually add some distance to it. So real simple here, I'm gonna use some simple variables we're gonna call local, and I'll say from point A to B, right? Which is going to be, doing parentheses here. We're gonna take 0.1, we're gonna subtract our 0.0 from it, and then we're gonna do dot magnitude. And then we're going to do a very similar thing, except this time it's from point B to point C, and this is going to be our 0.2 minus our 0.1 and dot magnitude. And then finally, I'm going to go and do local distance, because this is our final distance. And I'm able to use the distance variable here, even though we use the random distance function with the distance variable, because they're in different scopes, right? They're only in the scope of their own functions. So that's perfectly fine. So we're going to take AB, we're going to add BC. And that gives us our actual total distance from our start point up to our curve point to our end point. It's not going to be exact, of course, because again, it's not flying all the way up to it, but that's okay. We'll worry about that if we decide to try to make this much more realistic. I'm going to go ahead and shrink this down now. All right, so in our flightpath function, let's now call this function in our tween time. So instead of 0.3, we can just do speedcalc, and we have to fill in some positions. So we're going to do our start position, obviously, as our first position. Our second position is going to be the top of the curve. Now the top of our curve is going to be index 6 of our curve points table, as long as we're making 11 points. All right, so if we're making 11 points, right, our start point, and then 10 additional points, roughly halfway between that, but at the top of our curve, it just does end up being 6 points. So our sixth index would technically be the right way, but it will vary if we're using fewer points or more points. So for example, right now we're actually still generating 100 points, so obviously 0.6 would be very early on. That wouldn't really make sense. So our midpoint, we need to do a little bit more math here. And quite simply, we can just account for this by saying our curve points table, we're going to call an index by using square brackets, and we're going to do math.ceiling, which returns the smallest integer larger than or equal to x. So in other words, whatever result we're going to get from our math here, we're going to divide our curve, or the number of points in our curve, by 2, and then we want to make sure that we're getting a rounded up integer. So that's why we're using this math.ceiling here. So we'll go ahead and do number of our curve points, so basically the number of values in our table, and we'll divide that by 2. All right, so there is our second point, basically the top of our curve. And then our third position is going to be our final curve point value on the table, which again, is going to depend on how many points we're making. So we're going to call our curve points table and use the index of whatever the number of our curve points are, which will give us the final point in our curve points table. So while this gets us the total time for the seagull to travel from start to finish, we need to actually divide this by how many points there are, since the between time is how long it takes to travel from just one point to the next, not from the start to the end. So we're just going to go ahead and divide this whole thing by curve points. Or sorry, by the number of curve points, right? So let's go ahead and test this out. So if we run this, I have a error in my output. Let's fix that. So I made a mistake. I actually forgot that we're not actually returning anything here. In order to get our actual velocity or our speed calculation, we need to return our distance. Sorry, overspeed, which I apparently spelled with 3 E's as well. So let's make sure we fix that. Yeah. All sorts of mistakes in here. All right, so now when we run this, this should actually work, not give us any errors. Indeed, so you can see even with 100 points, it's taking its specific amount of time to get there. My bird is of course flying backwards because I have the angles multiplication here. So I'm going to go ahead and remove that from mine. Again, you will need to keep yours that way, however. Stop, restart this here just to show you how it should look in the end. There we go. And let's go ahead and also drop our number of points down to what we had before, because we don't actually need 100 points in our curve. Alright, so it takes that amount of time to fly point to point. Let's go ahead and increase this to something like 150, so we could fly 20 all the way to 150, and this should give us a good idea of the speed remaining consistent. I see, I had made another mistake. I put max height here, just filling in what it gave me instead of max distance. Alright, so now that explains why he was not flying very far, but there you go. So now you can see even at that distance, he's still flying at the same speed that he would if you were doing a shorter distance. And again, the speed is from point to point, not necessarily from start to finish, right? Okay, so set this back down to something like 20. We can now see a real random result. And you'll see that our curve is still completely straight as well. Perfect. All right, so nice. We can now mess around with the height and max distance values to get whatever results we desire, but otherwise that's all there is to it. If I was really going for a more realistic takeoff, I would make the seagull move forward a little bit before it lifts off the ground, since they tend to do a short jog to build up speed before taking flight, but in this case this meets our needs just fine. Besides, if I really wanted a realistic path, I'd be using cubic Bezier curves instead of a quadratic, but I didn't want that headache. So thank you once again for sticking with me through a couple long video tutorials. Moving forward, I'm going to try and work on getting some shorter videos out and see how those do. Make sure to subscribe, hit the bell to be notified of those future releases, as well as everything else I'm going to be uploading. And please leave a comment with your thoughts on how I'm doing so far, and if you have any requests for something you'd like for me to cover on the channel. Until next time, have a good one.